Okay, so we're moving on from PV equals nRT in this one, just for a little while, to a unique property of gases that means that it helps us do some calculations and sometimes comes up in questions that students overcomplicate. Okay, so this is something where sometimes a question will come up and you just need to sort of remember this property of gases. And it makes doing the questions a lot easier, and we will look at some of these questions more in class as well. But this is Dalton's law of partial pressures. Okay, so we've already talked about pressure, and we know that pressure is due to the collisions between the gas particles and the side of the container. So now we're going to look at what that means when we have different mixtures of gases. I do recommend you get on and have a go and watch this partial pressures video. I will probably play it in class anyway. It gives a really cute analogy about how the gases mix, and I've spoken to some of you about it and we will watch it. I'm not going to play it while I do this video. That's just a waste of time. We can all hop on and have a look at it at YouTube. So essentially what this means though, okay, is partial pressure. We are talking about pressure in terms of the overall pressure that is made up of the contributing pressures from different things. Okay, so each thing will have a partial pressure, and then we talk about the total pressure from all of them. And if we think back to kinetic molecular theory, okay, then where we have our 5 assumptions about how gases behave if they're acting ideally, then we know that the particles of a gas are all independent of each other, which means that if I put neon and oxygen and water vapor into a container, then they would all be independent of each other because there's no forces of attraction or repulsion between the particles. Okay, and we see this largely with the mixture of gases that we have in air. They're not all colliding and sort of reacting with each other all the time. What we've got is different gases existing in one particular volume, and because of that, it's the collisions of each individual gas that sum totally to make our pressure. Okay, so if we take a mixture of gases, all the molecules move independently and they all collide independently. So the total pressure of a system, it makes sense, would be the total pressure is going to be the pressure due to the first gas and how often it collides with the size of the container, the pressure of the second gas and how often it collides with the container, and so forth. So if we look at this diagram here, if we have a container that contains helium at 1 atmosphere or 100 kilopascals, and we had a different container with nitrogen at 1 atmosphere, and one with oxygen at 1 atmosphere, if I was to combine the contents of all 3 of these flasks into one single flask, I would still have oxygen molecules, and I would have nitrogen molecules, and I would have helium molecules, but the total pressure is the sum of the pressure of each gas. Remembering that for this I am keeping my volume constant, okay? So this is if these are all at the same volume, and of course it would go also that temperature is constant. Okay, so for temperature and volume being constant, what I'm going to do is combine each of these, and the pressure from each one adds up to the total pressure. And that should make hopefully some logical sense, because in this one I've got my heliums hitting the side, I can have my nitrogen hitting the side and my oxygen hitting the side, which means that my total pressure is going to be due to the sum of each one of these collisions. Okay, and this is just another diagram to show that in a bit larger detail. So if I have container A at 100 kilopascals, container B at 250 kilopascals, container C at 200 kilopascals, if I was to combine each of these into one container with the same volume and at the same temperature, the total pressure is simply 100 plus 250, which is 350, plus 200 is going to equal a total pressure of 550 kilopascals. Okay, hopefully that is fairly intuitive and makes a bit of sense. So let's just have a look at it, how a question may look for that, so we know what it looks like, and then this will be done. So the total pressure in a vessel containing a mixture of oxygen, nitrogen, and carbon dioxide is 110 kilopascals. So P total is equal to 110 kilopascals. Okay. And then the partial pressure, okay, so the partial pressure of oxygen, so P of oxygen, O2, is equal to 25 kilopascals. And the partial pressure of nitrogen, so the pressure, sorry about that, the pressure due to nitrogen gas is 83 kilopascals. Okay, they're all in the same unit, which is good. Okay, what is the partial pressure of carbon dioxide? So we want P of CO2. Okay, now if my total is 110, okay, it makes sense that the pressure of CO2 is going to equal 110 minus 25 minus 83. Okay, so if we do that, which I should be able to do in my head, 110 minus, sorry about that, 110 minus 25 minus 83, I get that CO2 is going to be 2. So the partial pressure of carbon dioxide is going to be equal to 2 kilopascals. Okay, so we've got 2 kilopascals happening here for our answer on that one, and my pen has decided to stop working. So hopefully that makes sense. Again, I will give you some more practice questions to be able to look at these, but that's it for partial pressure.